friends, welcome back to the online certification course on watershed hydrology. I am Rajendra Singh, professor in the Department of Agriculture and Food Engineering at Indian Institute of Technology, Kharagpur. We are in module 1 and this is lecture 4 and the topic is rainfall data analysis part 2. And in this lecture, we will continue with our discussion on the estimation of mean areal rainfall, and then we will talk about estimation of missing rainfall data. So, if you remember in the previous lecture when we started with the estimation of mean areal rainfall, we said that because in a rain gauge in a catchment we can have multiple rain gauges and each rain gauge gives a point rainfall. So, in order to get a represented value for the catchment, we need to estimate the mean areal rainfall, and there are 4 important methods: the arithmetic average method, Thielen polygon method and isohydral method. These 3 methods we discussed in the previous lecture. Today, we are going to start with the 2 axis method, another way of finding out the mean areal rainfall of the basin. Now, this 2 axis method was developed by Bartholomew in 1976 and it can be described in the following fashion. So, basically what happens is that in this case we need to have the watershed catchment delineated, and also we should have the outlet identified. This is the basic requirement, that you have to have delineated area of the watershed with its outlet located, which is typically available data. So, first thing we have to do, because it is a 2 axis method. So, we have to draw the 2 axes which are referred to as major and minor axis of the watershed, and this is the procedure. So, first thing what we do is that we join the watershed outlet to the farthest point on the boundary by straight line, which is line OT in this figure. So, this is our outlet. So, we locate the farthest point on the boundary of the watershed. In this case, let us say this point is T, and so we draw a straight line joining these 2 points OT. Then we draw a perpendicular bisector to this line, which is line AB in the figure. So, this line AB, perpendicular bisector to this line OT, is line AB, and this is referred to as the minor axis. And then we draw a perpendicular bisector of the minor axis to, that is, say, line CD in the figure. So, and that way we get the major axis. So, the procedure I repeat: first thing we do is that knowing the outlet, we try to locate a point on the basin boundary which is farthest from the outlet, and we draw this with a straight line OT, in this case straight line. And then we draw a perpendicular bisector. This is line AB, and this line is the minor axis, one of the axes which we are referring to. And then we draw a perpendicular bisector of that line CD, in this case here, which is referred to as the major axis. So, basically what we do is that in this method, first we locate the major and minor axis of the watershed. Then comes the next procedure. We need to determine angle theta for each station by referencing its station 2 axis. So, for example, this is station P1 which has recorded rainfall, that is a point rain gauge installed in the basin. So, what happens is that we draw straight lines joining this station to 2 axes, but the farthest point of 2 axes. So, for example, if you take P1 and if you take the minor axis AB, then if you consider PB and PA, so PA is larger than PB. So, that is why we will join draw a line joining P1 to A on the minor axis. Similarly, we will try to find out which is the farthest point of the major axis with reference to this station P1. So, here in this case D and C, of course, C is farther away. So, that is why we will draw a line joining P1 to C, and this angle, acute angle between lines joining P1 to farthest end of 2 axes, that is P1A and P1C in this case, that is the angle of interest for us. So, of course, this angle can be, we can determine this angle theta either mechanically by a protector, or we can use mathematical equations. So, because we know we have located the 3 points A, B, C, and we know the distance in A, B, C between them, because we know the coordinates. So, we can find out the distances by using this relationship. So, length L of joining any 2 points whose coordinates are x 1 y 1 and x 2 y 2 is given by this relationship. So, we can find out these lengths, and once these lengths are known, then in this triangle ABC, angle theta at A, that is angle which is being made at point A, is given by this relationship, that theta is r cos or cos inverse b square plus c square minus a square by 2 ABC, where A, B, C are lengths of sides opposite angles A, B, C respectively. So, we know A, B, C. So, obviously, accordingly, when we are finding out value of theta at A, then we know where will be the position of A here. So, similarly, we can find out all 3 angles using this relationship. Therefore, in this figure, if we come back to this figure with point A, where we join P1 to A and P1 to C. So, that means we know the lengths P1A, P1C and AC, that is these 3, because we know the coordinates, we can find out the lengths, and then this theta at P can be found out as AP1 square plus P1C square minus AC square divided by 2 AP1 to P1C, and quantity in parenthesis is the length of the line. So, that we have already shown. So, AP1 is the length of the line joining these 2 points corresponding to this figure also. ABC we have already defined in this figure. So, in here important point is that theta is obtained in radians, and in order to convert that into degree, we have to multiply with 180 by pi. That is the thing you have to remember, that we get the theta in radians in this case. So, that is important point to remember. Now, what we do next is that we determine the station weight for each rain gauge, and this is the ratio of the station angle to the sum of all station angles. So, for a particular station theta I and sum of all theta I, that so basically here the weighing factor or weight is assigned based on the weight a particular angle makes compared to the total weight in the station, and the mean rainfall is computed using this relationship, where r bar is I 1 to n W I P I, where W I is the weight assigned to that particular station and P I is the rainfall that is recorded at that particular station. Now, based on there are certain features of this method. It is based on the assumption that all rain gauges are not equally significant in regard to mean annual rainfall. A rain gauge located near the center of the watershed should be weighed more than one located farther out, and the weight of the rain gauge depends upon its location with respect to 2 axes of the watershed. So, that simply means that if you have a watershed and there are 2, suppose we have located the major and minor axis, and suppose we have a rain gauge station here at this point A at the center, and a station here say station X. So, obviously, if this station we have to join the farthest points. So, this is the farthest point and this is the farthest point. So, this is the angle theta for station A, where in this case the farthest point is this one and the farthest point on D1. So, this is theta of x. So, you can see that the weight assigned to this theta A will be much larger compared to theta x. So, that is how a rain gauge which is located in the center, that is more representative of rainfall of the mean areal rainfall, that is why it is given more weight. So, that is the feature of this particular method, and this method is fast, efficient and easily amenable to computer programming. So, you can easily write a computer program and use that to measure the rainfall using this method. Now, coming to an example, there are 3 rain gauge stations available to characterize the rainfall of a catchment whose shapes can be approximated by straight lines joining the coordinates. These are the coordinates given of the boundary of the catchment, and also the catchment outlet location is given, that is, it is located at one of the points. The coordinates of rain gauge stations and the annual precipitation recorded in 2023 are tabulated below. So, there are 3 rain gauge stations, these are their locations and these are the annual rainfalls recorded in the stations. Determine the mean rainfall of the catchment by 2-axis method, that is what we have to do. Now, coming to this method, 2-axis method and application to this particular problem. So, what we have to do is join the given coordinates of the catchment boundary by straight lines. So, this is we are because we do not know their true shape. So, we are approximating these catchment boundary by drawing straight lines. So, these are various coordinates here and they are joined by straight lines. And we need to locate the rain gauge using their coordinates P1, P2, P3. So, P1, P2 and P3 are 3 rain gauge stations, which coordinates are given. Now, we have to follow the procedure. First thing we have to do is determine or locate the 2 axes, minor and major axes, and the procedure, I repeat, was that we join the watershed outlet to farthest point on the boundary by straight line. So, obviously, this is our outlet here. This is outlet, and so with reference to that we will find out the farthest point, which is y in this case. So, we will draw join these 2 points x and y by straight line. We draw the perpendicular bisector to that, which is point line AB here, which is nothing but the minor axis. Then we draw a perpendicular bisector of this minor axis AB, and that particular line is CD, and that is nothing but the major axis. So, AB is the minor axis and CD is the major axis that we have located. So, we have located the major and minor axis, which are one of the first requirements of this particular method. Now, what we do is that we draw straight lines from gauging stations to farthest ends of 2 axes. For example, if station P1 we talk, then obviously minor axis if you consider, then B is the farthest point. If you consider the major axis, D is the farthest point. So, that means we will join lines P1D and P1B from station P1. Similarly, from P2 we will join the P2B, P2D. For P3 we will join P3C and P3A. So, they will be joined to farthest points of these 2 lines, and obviously we know the coordinates of all these points, because the coordinates, once we draw the minor and major axis, we can find out the coordinates of these points. So, we know the coordinates of all these points. So, for P1 the relevant distances are P1D, we need to get P1D, P1B, and of course, the distance between these PD. So, knowing these coordinates, we can find out these distances. And once the distances are known, then we can, for station P1, we can calculate the value of theta 1 using this relationship. We already saw arc cos or cos inverse, and P1D square plus P1B square minus BD square, which is the length in front of this angle theta, that is angle theta here, theta 1 here in this case, and of course, 2BD, P1D, P1B. So, we know these distances. So, we can find out the value of theta 1, which comes out to be 71 degrees. Remember that we got the values in cosine and then we converted. So, this theta 1 is 71 degree. Similar exercise will be done for station P2 and P3 also. And so, likewise theta 2 comes out to be 101 degree and theta 3 comes out to be 71 degree. And then of course, we need to calculate the weights for different stations, and weight is given by Wi by theta I by sum of theta I, and mean rainfall is R bar Wi Pi sum. So, here the calculations are shown here. So, we have found that theta 1, theta 2 and theta 2 for P1, P2, P3 are 71, 101 and 71. The total angle theta is 243. The weight will be nothing but 71 by 243 for this station. So, this is nothing but 71 divided by 243. This is 101 divided by 243 and the third one is 71 divided by 432. So, we get the weights. The rainfall values already are given in the table. So, we get the multiplication of Wi Pi for each station. So, multiplied by Wi and Pi to get this value and this value. This is a point, of course, and the sum value will be nothing but this is. So, 1102.32. Thus, the mean areal rainfall of the catchment is 1102.32 millimeters following this particular method, that is mean two axis method. So, little it appears little longer, but it can be programmed easily. So, this is a popular method also for finding out the mean areal rainfall. Now, we come to estimation of missing data. Now, as I mentioned that we in one previous lecture, I gave you the sources of rainfall data. That rainfall data can be procured from many sources, and one major source in India is India Meteorological Department, IMD. So, obviously, you can download the data from their site or you can procure the data which they provide typically in CD. Now, many times when you start using the rainfall data, you will find that many rainfall stations have incomplete record. So, that means sometimes you may find that you are dealing with say 1 year data. So, in the month of May 10 days data are missing, or in the month of December 5 days data are missing. And so, missing data is a very common phenomena, and that means records are mostly incomplete. So, in that such a situation, it is often necessary to estimate the missing data to utilize these partial records, especially in data scarce conditions. So, if you have huge amount of data in a particular state, in a particular place, at a particular place to analyze, then you may discard one or two, but when you are dealing with only limited data, then obviously it becomes essential to estimate the missing data. So, to be able to utilize the rainfall record which we obtain. And basically, in order to estimate the missing rainfall data, we use the corresponding data of the neighboring stations for estimating this missing data. And there are different methods of estimating the missing rainfall data, that is arithmetic average method, normal ratio method and inverse distance method. And we will see these methods one by one. So, first method is arithmetic average method. Now, if the normal annual rainfall of the surrounding stations is within 10% of the normal rainfall at station X having missing rainfall data. So, basically what happens that in a catchment, this is, let us say this is the rainfall the data where we are analyzing, and we find that there is a missing record. So, what we will do is that we will collect the corresponding data of a particular day or a particular week, whatever analysis we are doing from the neighboring stations. And the first analysis what we do is that we analyze the normal rainfall, normal annual rainfall of these stations. So, normal rainfall is basically a data average rainfall over a long period of time, and typically we use 30 years of record for finding out the normal rainfall. So, if we know the normal rainfall of this station X and the neighboring stations, then we analyze and whether what is the variation of the normal rainfall at this particular X with corresponding to other neighboring stations. And if this value is within 10%, that is, if the normal rainfall of station X is within 10% of the normal rainfall of surrounding stations, then basically we can take a simple arithmetic average of the data recorded at the neighboring stations to fill that missing record in the station. So, that is pretty simple. So, in that case R1, R2, R by the sum we obtain and divide by the number of neighboring stations or surrounding stations. So, that is pretty simple, but this condition has to be fulfilled. The next method is normal ratio method. In this method, normal rainfall of station X and the surrounding stations are used to determine the weights for the surrounding station. So, in this case you see it is arithmetic average. So, weight assigned is equal. So, 1 by n is weight, but in normal ratio method it is the normal ratio of the normal rainfalls of this station X and the neighboring stations. So, basically in this case R bar is the normal rainfall. So, R x bar and R a bar or R x bar R b bar, that assigns the weight. So, in this method the normal rainfall of station X and surrounding stations are used to determine the weights for surrounding stations, and then missing rainfall record is calculated using this relationship. So, basically it is nothing but the weight assigned multiplied by the rainfall at that particular station divided by the total number of stations. Let us take this example 2 on the estimation of missing rainfall. So, rain gauge X was not operational during a storm. The rainfall amounts at 3 adjacent stations A, B and C during the storm were 37, 42 and 49 millimeters. The normal annual rainfalls for the gauges are tabulated below. Estimate amount of rainfall station X during the storm. So, this is station X where we want to find out the missing rainfall and the corresponding values at neighboring station A, B and C are given here, and the normal rainfall of all the 4 stations are available with us. So, in order to get the missing rainfall data, first we need to determine the appropriate method for estimating the missing data by finding the variation of normal rainfall of neighboring stations with respect to normal rainfall at station X. So, normal rainfall of station X is given at 694 and 10% we look for 10% variation. So, 10% of Nx is 69.4. That simply means that the range comes out to be 624.6 and 763.4. So, that means the normal rainfall of neighboring stations should be within this range in order to use the arithmetic average method, else we have to use the normal ratio method. So, since the normal rainfalls of the neighboring stations, that is 726, 754 and 760 are within this range, that is 624 to 763, then we can use the arithmetic average method. And in this case, as we saw that weights are assigned, equal weights are assigned. So, it is pretty simple. The average rainfall will be sum of the rainfalls at neighboring stations divided by number of stations. So, it is 37 plus 42 plus 49 divided by 3 or 42.7 millimeters. So, missing rainfall at station X during the storm is 42.7 millimeters. So, that 2.7 millimeter will put in the record collected for station X, and then the further analysis will be done. Then comes the take another example. Let us take one of the 4 monthly rain gauges in a catchment developed a fault in a month when the other 3 gauges recorded rainfall of 48, 58 and 69 mm respectively. If the normal annual rainfall of broken gauge is 707 millimeters and that of the 3 surrounding gauges is 741, 769 and 855 millimeters respectively, estimate the missing monthly rainfall for the broken gauge. So, again we have the data available for 3 surrounding stations and the normal rainfall for all 4 stations. So, again we have to find out the 10% range. Now, in this case for problem stations, for station X for which we have to find the missing data, the normal rainfall is given as 707, 10% of that is 70.7. That means the 10% range for Nx is 636.3 mm and 777.7 mm. That means this is the cutoff in order to decide the method for as far as the normal rainfall at neighboring stations are concerned. Now, if we look at the values of normal annual rainfall at neighboring stations, we find that there is a value of 855 which is beyond this range. So, that means the normal annual rainfalls are not within the range. So, we cannot use the arithmetic average method and we need to use the normal ratio method, and that is what we will use here. So, in this case the formula is given. We can also do like we can calculate the weights outside for each station, that is by normal rainfalls of station X and A, B, C, but combined you can use the formula like this, where values of R A, R B, R C are the recorded rainfalls, bar represents the normal rainfalls, and number of stations is 3. So, by putting the values here, we get R x value of 52 mm. That means the missing monthly rainfall at broken gauge is 52 mm. So, this data, as I already mentioned, it will be filled in the record, and then subsequent analysis using the other data will be done. Now, we come to the next method, which is inverse distance method. Now, in this method, the distance between the station X and the surrounding stations is used to determine the weights for the surrounding stations. So, that simply means we have to rely on the weights find, and the weight assigned to a particular station is given by 1 by d I square, where d is the distance between the station X and the neighboring station. So, in this case what happens that suppose this is the problem station X and these are our neighboring stations. So, first thing we have to do is measure the distances. By knowing the coordinates, we already know we can easily calculate the distances between 2 points. So, these distances d 1 to d 5 are estimated, and once distances are there, then we can find out the weights assigned to different stations, and then using this equation where numerator is sum of P I W I and denominator is sum of the weights basically assigned to different stations, and using this we can find out the missing rainfall at station X. Now, let us take an example on this. Rainfall recorded at different rain gauges in event are tabulated below. Rain gauge A, B, C, D and E. Their coordinates are given 2, 3, 2, 8 and so on, and the rainfalls recorded at these stations are also given here. It was noticed that rain gauge X, which is located at 5.5, that is the coordinate of this particular rain gauge is given here. It was not operational during the event. Determine the missing rainfall at station X using the inverse distance method. So, that is the method we have to use in this case. Now, we know the stations, we know their coordinates, and we have been given their rainfall values. So, obviously, we know most of the things, and so rain gauge stations are plotted using the given coordinates, and we can find the distance between the rain gauges by this formula. We already have used this. So, for example, the distance of rain gauge station A, which has a coordinate of 2, 3, and station X, which has a coordinate of 5.5, can be calculated by this relationship using this. D 1 is 5 minus 2 square plus 5.5 minus 3 square, and it comes out to be 3.91 kilometers. And we know that the weight is 1 by d I square. So, weight for station A will be 1 by d 1 square. So, that comes out to be 0.066. So, that is how we can assign the determine the weight assigned to this particular station. So, using the similar procedure, we can determine the distance and the weights for different rain gauge station B, C, D and E as well. And then obviously, we need to calculate the P I W I. So, distances shown here, station A we already calculated this. These are the distances for other stations B, C, D and E. So, this is station A, which we already calculated. This is for B, C, D and E. So, these are the distances, these are the weights we calculated, and this is the P I W I, and sum of W I is this, sum of P I W I is this, and we know that the ratios of these two, that is missing rainfall at station X, can be obtained by finding out the ratios of these two. So, 25.350 divided by 0.365 gives us a value of 69.5. So, missing rainfall at station X is 69.5 mm using the inverse distance method. So, with this we come to the end of this chapter, where we saw the 2-axis method for determining the mean annual rainfall, and then we saw the 3 different methods of estimating the missing rainfall record. I hope you got the points. In case of any doubt, please raise questions on the forum, and also please give your feedback so that we can improve things. Thank you very much.